example that we have in the previous class. So in the previous class, we were trying to solve this equation, right? So you have minus u second minus 2b u prime is equal to lambda u on 0, 1. u0 is 0, u1 is 0, and b is greater than 0. So this is what we worked last time. So after this example, I'm gonna go back to the differential equation, and I'm gonna try to show you how we derive these three cases. I mean, for this, no, you don't want that? Some of your friends requested that, so. So I'm gonna try to. I know that some of you know that from previous class, but the others don't remember. So I'm gonna try to go back to differential equation, and I'm gonna try to show you how we get these three cases to solve a second-order differential equation with constant coefficient. All right. And after that, I'm gonna go back to linear algebra to show you the spectral theories. I mean the spectrum of a matrix. Right? So those are the knowledge from the previous class. But I mean I put a message on Canvas yesterday, and I got some requests. So I'm gonna go back and review all of those things for you. I know that some of you know this, but the others don't. I mean the others don't remember. So it's better that we go back and try to make sure that everyone understands. All right? So this is what we were trying to solve. So we have this spectral, this eigenvalue problem, and we were trying to solve. So we have three cases. We consider b square. So in the last time, we consider x squared plus 2bx plus lambda is equal to 0. So this is the characteristic equation. All right, so this is the characteristic equation, and we were trying to consider the three cases of this equation. Case number 1 is b squared minus lambda is greater than 0. So in this case, you have trivial solution. This is what we solved in the previous class. If b squared minus lambda is greater than 0, you have a trivial solution. Case number 2, if you have b squared minus lambda is negative, then you have trivial solution as well. So this is what we did in the previous class. So the last case is case number 3, in which b squared minus lambda is negative. All right? So I explain again. In the previous class, we considered the characteristic equation of this eigenvalue problem. You have x squared plus 2bx plus lambda is equal to 0. You consider three cases. b squared minus lambda is greater than 0, so you have a trivial solution. b squared minus lambda is negative, you also have a trivial solution. The last case is b squared minus lambda is negative. This is what we are going to cover in this class. Yes?
Case 2 is supposed to be equal to 0?
So, very good. Can you sign the paper, please? So after solving this example, I'm gonna go back to differential equation theory, and I'm gonna show you why we have these three cases. All right. So this should be something from previous class, but I'm gonna explain it again so that you have a full understanding of the theory. Now, if b squared is minus lambda is negative, you have two solutions, right? Two roots. So the first root will be minus 2b plus 4b squared minus lambda over 2. And this gives minus 4 lambda. And this gives you minus b plus I, the square root of lambda minus b squared. This is the first root. So the first root is similar to the case when b squared minus lambda is positive. You still have minus 2b plus the square root of 4b squared minus 4 lambda over 2. So this gives me, but this in this case b squared minus lambda is negative. Then you have minus b plus I square root of lambda minus b squared is positive. The second case is minus 2b minus 4b squared minus 4 lambda over 2. This gives me minus b minus I square root of lambda minus b squared. So where is this I coming from? Because in this case b squared minus lambda is negative. So square root of b squared minus lambda will be square root of lambda minus b squared, which is positive times I. Right? So I is a number when you square this I, you get minus 1. Questions? It's clear? Alright, so I explain again. In the last case, b squared minus lambda is negative. You also have two roots. So the two roots in this case will have this form minus b plus I square root lambda minus b squared and minus b minus I square root lambda minus b squared. Alright? So then from these two roots, you're going to have two solutions. So the first solution will be exponential of minus bx cosinus of square root of lambda minus b squared x. And the second solution will be exponential of minus bx sinus of square root of lambda minus b squared x. So these are the two solutions that you have. The first one will be the exponential of the real part, right? So this real part will give you the exponential. And this imaginary part will give you the cosinus and the sinus. It's good? Question? In a minute, I'm going to review to you where all of those formulas are coming from. Right? So, I explain it again. When I solve the characteristic equation, which is the second order algebraic equation, I have two roots. In this case, b squared minus lambda is negative, so the form of the roots will be the same. It's going to be minus 2b plus the square root of 4b squared minus 4 lambda. But in this case, b squared minus lambda is negative, so you're going to use the I number. Alright? So I is a number in which I squared is minus 1. Then you're going to have minus b plus I square root of lambda minus b squared and minus b minus I square root of lambda minus b squared. From this root, you're going to take the real part to be the exponential part, and the imaginary part will be the cosinus and sinus part. Questions? It's good? In a minute, so this is something that is coming from differential equation cos 3133. But I'm going to go back to this and explain to you where all of those formulas are coming from. Now, you have two solutions, right? So the general solution will be u1 of x times the constant c1 plus c2 times u2 of x. So the general solution will be the linear combination of u1 and u2, and you have to find c1 and c2 using the boundary condition. Again, I have a reminder for you that I just put the homework 3 online, and homework 3 will be the same kind of thing. You have to solve the eigenvalue problem using all of those ideas. And one of them is very similar with the last questions in the midterm. So in the midterm, I said that this was in the solution was in homework was a problem that we solved in class, and I recorded it online. So I didn't write down the solution, right? But it's on the video. So you watch again the two videos on March 6 and March 8. You know how to solve it. And after you submit this homework 3, I'm gonna write down step by step all of the details of that solution, of that problem. All right? Right, so Ux is C1 U1 plus C2 U2. So this is going to be the solution of this equation, but now I have to check the boundary condition. So the boundary condition number 1, U0 is 0. So when U0 is 0, what I have is the following. So I'm going to replace 0 into all of those formulas. So I'm going to have 0 is equal to C1 exponential of minus b times 0 cosinus of square root of lambda minus b squared times 0 plus exponential of minus b times 0 sinus of square root lambda minus b squared times 0. So the first boundary condition, this is C2. The first boundary condition can be satisfied if you replace 0 into all of the x. So you're going to have 0 is C1 times exponential minus b times 0 cosinus of 0 plus C2 exponential minus b times 0 sinus of 0. So cosinus of 0 is 1 and sinus of 0 is 0. So this gives you 0 is C1, this is 1, this is 1 plus C2. So this is 1 and this is 0. So this gives you C1 is 0. Questions? It's clear? So from the first boundary condition, you're going to get Ux is C2 exponential of minus b times x sinus of the square root of lambda minus b squared times x. After solving the first boundary condition, C1 becomes 0. You replace 0 into the general form of U, you get only the second term with C2. Alright? I explain again. After solving the characteristic equation, in this case, you're going to have exponential and cosinus, and exponential and sinus. Now, the general solution will be the linear combination of these two solutions. Alright? What I'm trying to do now is to check the boundary condition. First boundary condition. So I'm going to have U0 is 0. So U0 is 0 means that I have to replace in all of the x here, x to be 0. So when I replace x to be 0, I'm going to have 0 is C1 times 1 plus C2 times 0. So this gives me C1 is 0. I plug C1 is 0 back into the form of U. This gives me C2 only, the term that contains C2 only. Question? Now, I'm going to use the second boundary condition. Boundary condition number 2. U1 is 0. This means that 0 will be C2 exponential of minus b sinus of square root of lambda minus b squared times 1. The second boundary condition will give me this one, because I'm going to replace x to be 1 here. Question? It's good? Right? So you have the general form of the solution. You replace x to be 1. I'm going to have C2 exponential minus b times sinus of square root of lambda minus b squared times 1. All of those are constant, so I have sinus of square root of lambda minus b squared is 0. This means that lambda minus b squared is n pi. And n should be 1, 2, 3. So then you're going to have lambda minus b squared is n pi squared, and lambda is b squared plus n pi squared. Alright? Questions? So I explain again. For the last case, you're going to solve the characteristic equation. You're going to find two solutions. In this case, the two roots have the same formula. The first one is square root of b squared minus lambda, and the second one is minus of b squared minus lambda. But in this case, b squared minus lambda is negative. Because this is negative, you're going to have to put the I there. Because of the I, you're going to have exponential of the real parts and cosinus of the imaginary part. And exponential of the real parts and sinus of the imaginary part. So I'm going to explain to you in a few minutes, because I'm going to recall to how we derive all of those formula. So I'm going to tell you why we have sinus and cosinus in this case. So who knows why we have sinus and cosinus? Yes?
Because of the conjugate pairs, so you take the... Never mind.
Excellent. Yes, this is a yes.
Euler's equation?
Sorry?
Euler's equation? The Euler's equation?
Euler equation?
Yeah, for E.
Right. Excellent. Yes. Yes. So those are the good answer. Can you sign the back up, please? Both. All right. So this is because of the Euler formula. All right. But I'm gonna go back to that. Now because this is the general form of the solution, I'm gonna take the linear combination of C1 and C2, and now I'm gonna solve for C1 and C2. All right. U0 is 0. So I go back to this boundary condition. U0 is 0. When U0 is 0 means that I have to replace 0 into all of the x, and I find C1 is 0. I plug it back to the general formula, so I get rid of the terms that contain C1. So I'm going to use the second boundary condition, and I find that sinus of square root of lambda minus b squared is 0, which means that lambda minus b squared is n pi. So lambda has to be b squared plus n pi squared. All right? So conclusion. The eigenvalue lambda n has to be b squared plus n pi squared, and eigen functions, eigenvectors, will be phi n of x, or un, whatever. So I'm gonna call un of x will be. So this is it, right? So this is gonna be sinus of square root of lambda n minus b squared x, and this is sinus of n pi x. All right. So this is the eigenvalues. This is the eigenfunctions. So at the final step, this is lambda n, and you plug it back to this u, and you find sinus of n pi x. Yes.
Using the exponential.
Excellent. Yes. Based on the exponential. Yes. Based on this exponential. Yes. Exponential e to the minus b. Can you sign the back of this? It's clear? So you understand this problem 3. So you see that the first example of chapter 3 will be similar to this. But before going to that, because some of you forget what was going on in differential equation class 3133, I know that some of you know very well like Ian, but let us go back to differential equations to understand where do we get all of those formula, all right? You agree with that? Or you don't want to review that? So who wants to review that? No one wants to. Who don't want to review that?
Do not.
Yes.
Don't we not? Or?
Not. Who don't want to review differential equation?
Were you sure you're doing how we get to the formula?
How we get to those formula? No, you don't want to.
Do we need to show it?
You don't need to.
Okay.
So those are the formula that you have, and I gave you the formula.
Yeah.
So if we just memorize that.
You have to only to memorize all of those formulas. So you don't want to review it. All right. So 2 versus 4. All right.
I have a question for, so when we get our eigenvalue, if in this case C1 wasn't 0, would cosine also be part of the eigenvector?
Yes. So if C1 is not 0, so yes, very good question. So remark, if we find lambda n is n pi, right? And C1 is not 0, and C2 is not 0, all right? So the solution will be U x is C1 exponential of minus bx, right? Cosinus of square root of lambda n minus b squared x plus C2 exponential of minus bx sinus square root of lambda n minus b squared x. So this gives you C1 exponential of minus bx cosinus of n pi x plus C2 exponential of minus bx sinus n pi x. All right. So you see that if C1, so here I can prove that C1 is 0. But in the case that C1 is not 0, the general solution will be this one. So with this lambda n, you have this general form C1 times this function and C2 times this function. All right? C1 and C2 can be anything. So in general, in this case, for lambda n is n pi square, the equation u second plus lambda n u is 0 with some other boundary condition. It shouldn't be the same boundary condition. With the same boundary condition, C1 is 0, right? This equation has the general solution of the form C1 exponential of minus bx cosinus n pi x plus C2 exponential minus bx sinus of n bx. Right? So this is a vector space with basis exponential of minus bx cosinus n pi x and exponential of minus bx sinus of n pi x. All right. So C1 and C2 at any constant. All right. So this is the vector space with this basis. All right. So the two. So we have two eigenfunction, eigenvector. Exponential of minus bx cosinus of n pi x and exponential of minus bx sinus of n pi x. All right. So in this case, you can choose C1 and C2 to be anything. So this means that this is a vector space with two vectors to be the components of the basis. So you have two eigenvectors, this and that one, associated to the eigenvalue. lambda n is n pi squared. All right? Questions? It's clear? So I explain again. So in the case that you cannot prove that C1 is 0 and C2 is not 0. So the general solution will be C1 times this function plus C2 times this function. C1 and C2 can be anything. So you have a class of solution, all right? So you have a lot of solution of this form. So for instance, one of the solution is exponential of minus bx cosinus of n pi x plus 2 times exponential of minus bx sinus n pi x. All right? Another one is 3 exponential of minus bx cosinus of n pi x minus exponential of minus bx sinus n pi x. So anything like this, there are solutions of this equation. Right? So in general, you're gonna pick this and this to be the basis of the vector space. So with these two bases, you can multiply with any constant and you sum them and you get a solution. So basically this is, because they form a basis. So in this case, you have two eigenfunctions. The first one is this one and the second is this one. All right, questions? It's clear? Other questions? All right, so another thing. Do you want me to review linear algebra? No. No.
In what regard?
So, sorry?
Like in what regard? What do you mean? Like towards what end?
So I'm gonna, because we are talking a lot about vector space and basis and everything. So if you want me to review what is a basis, what is a vector space, what is an eigenvalue, what is an eigenfunction, I can take a whole class, one class, and explain to you again what are they. All right, so if you think that you can go back to those material and review it by yourself, then it is fine. So you can go back by yourself? You don't want me to review it? So who want to review it? Who don't want to review it? All right, so we don't review it. All right, so but make sure that you go back and remember all of those things. All right, so let us go to chapter 3. All right, in chapter 3, we're gonna have, we can start with a very similar question to this. Right. So, chapter 3, unit 3. All right, so we have the following problem. So you have ux plus 2ux is minus fx. All right? And here you have u0, 0, ul is 0. All right, so we need to solve this problem, all right? So this is a very similar problem to what we have before. So in this case, you have a similar equation. So you solve this equation on 0L. And we want to solve a very similar problem. You have uxx plus ux plus mx is 0. All right, and this is u0 is 0. So the first boundary condition is Dirichlet. And the second boundary condition is also Dirichlet. So using the standard method, the first step is what? you sign the paper, please? Step number 1, you solve the eigenvalue problem. So you're going to have Px. All right. So now we're going to have to solve the eigenvalue problem. So what is the form of the eigenvalue problem? So in order to identify the form of the eigenvalue problem, you have to know what is the operator. All right. What is the form? So to know the form of the eigenvalue problem, you have to identify what is the operator. So in this case, what is the operator?
Double prime plus two prime.
Excellent. Yes. Can you sign the back? So the operator will be everything that depends on you. All right, so the operator will be everything that depends on you. The fox or the source term or the fox. So everything that also depends on. All right. So you're gonna pick up everything that depends on you, and the leftover is the fox or the source term. All right. So in this case, you're gonna have u prime prime of x plus 2u prime of x plus fx is 0. All right. So this is depends on you. And this is independent of you. All right? So the operator, I'm going to call it L. All right. So in this case, the operator will be u second of x plus 2u prime of x. So one of the students asked me, why do I have 0 now? So what is the meaning of this interval? This is a basic question. Before we solve this equation, we have to understand first the meaning of this equation. All right? So what is 0 and L? It's the domain, right? So why do we need the domain?
So we know we're integrating.
Yes. Yes. So this is a very good answer. Can you sign the back of the paper, please? So this equation means that we have to find a function u such that u prime of x plus 2u prime of x plus is equal to minus fu. This is given when x is inside 0 now. All right. So this equation means that I give you a function f. You have to find this function u such that u second of x plus 2u prime of x is minus fx. All right. But in this case, you have two conditions at 0 now. Why do we need two?
So in the unique solution.
Yes. This is something that we discussed in the previous class, right? Can you sign the back of the papers, please? But u0 is 0 and 0 and ul is 0 and l. All right. So we need two boundary conditions because the solution is unique. So we want a unique solution. All right. So recall that on the first order equation, order equation. U prime of x is equal to ux. All right. So we on the so this equation needs only one boundary condition. U0 is 1, for instance. To have a unique solution. All right, because you have u prime of x is ux on 0 to infinity, and then u and 0 is 1, for example. All right, so in the previous class, we explained that for first order differential equation, or first order PDEs, for instance, you need only one boundary condition, right? Because this is first order. You have u prime of x is ux, and you only need one condition. So this is second order, so you need two conditions. So what happens if I put three conditions here? What happens if I put another boundary condition, another condition here? So I want a function that satisfies this equation on 0 and L. And 0 it should be 0, and L is should be 0, and L over 2 is 5. What happens if I put another condition and L over 2, for instance? Sorry? Depends what? Mm-hmm.
It could be a zero function or just order function.
Right. So this condition is so you need these two conditions to find a solution to the whole system. All right. So after you find a solution, you know exactly what is L over 2. So if you replace it here and it is not 5, then there is no solution, right? So for second order equation, you only need two boundary conditions. For first order equation, you need one. All right. So and the boundary condition in the first order differential equation, what is the different name for this one? Initial condition. Yes, because you only one you have only one point, so this is called initial condition, right? This is the initial condition. Right? Can you sign at the back of the paper, please? All right. So as Chris said, if you have only one point that you want to satisfy the condition, this point is the initial condition, right? So initially the solution should be like this. So if you have 2 points, it is boundary condition. But if it is 1 point, this boundary condition becomes the initial condition, right? So those are the concepts that we better understand before solving the equation. Questions? It's clear? All right. So this is basically the operator. Now, after identifying the operator, the next step is what? Is to find the eigenvalues and eigenfunction. So, step number 1. Eigenvalue problem. You're gonna have L of phi plus lambda phi is 0. And then you're going to have phi 0 is 0, phi L is 0. So this means that you're going to have phi second of x plus lambda phi prime of x plus lambda phi x is 0, and then phi of 0 is 0, phi of L is 0. Right? So I explain again. So you identify what is the operator, all right? So from the operator, you're gonna try to solve this eigenvalue. Sorry, it's not 2. So this is phi second plus 2 phi prime plus lambda phi is 0 with the two Dirichlet condition. All right? So what is the meaning of this eigenvalue problem? So why do we need the eigenvalue? And eigenfunction. Or eigenvectors.
Because if the operator is a self-adjoint, they need an eigenfunction basis in order model.
Right. Right. This is something that this is very good. But this one, yes, very good remark. We need the eigenvalues and eigenfunctions because in this case, if we can have the eigenfunctions, that will form a basis for the solution space. All right, because the eigenfunction, the eigenfunction will form a basis for the space of solution. Solution space. All right. So in linear algebra, this corresponds to the fact that if you have a matrix, so similarity to linear algebra. So if A is an n by n matrix, then there are n vectors Vn. This is eigenvectors, and n real numbers. Lambda n, v1 to vn, sorry, and lambda 1 to lambda n, such that, all right, so you have A, v1 is lambda 1 v1, and A, vn is lambda n vn, and v1 to vn forms an orthogonal basis for iron. All right. So in linear algebra, yes.
It's not important here, but can't you have imaginary eigenvalues?
Yes, you can have. Because yes. So if you look into the characteristic polynomial, you can have imaginary. So the condition here is that A has to be symmetric. All right?
Oh.
So the condition that all of those are real numbers. And this form an orthogonal basis is that A is symmetric. Condition is A is symmetric, and the condition in the other case is L is auto-adjoint, or self-adjoint. But I'm gonna do the computation, but at the end of the day, when I solve this eigenvalue problem that I just mentioned to you, all of the functions here, they are not orthogonal. And the reason is that this operator is not self-adjoint. So in the case that this is not self-adjoint, you have to use a different method. All right? But before going to that, I'm gonna show you that, okay, I can solve this one. I can still solve this one, but when I find a phi n, all of them are not orthogonal. So this is useful. This is similar to this case. So in linear algebra, if you look into an n by n matrix, so then n vectors v1 to vn, which has the eigenvectors, and n real numbers, lambda 1 to lambda n, such that AV1 is lambda 1 v1, AVN is lambda n vn, and those vectors are orthogonal. So it's from an orthogonal basis of I. But this happens only when I is symmetric. But if I is not symmetric, what happens? You can see that this lambda n, they can be not real. So they can be like complex number. When you have complex number, those v1 to vn can be non-orthogonal, and that destroy everything. And similarly to this case, you can have, you can still solve this problem, but all out of n are not orthogonal. So you need a different method. All right. So this is something that comes from linear algebra, and you better review this. If you want, I can do it, but according to the rules, you don't want it, right? But I'm gonna put something on Canvas so that you can go back to this and read it. Right? So I'm not going to review it, but I'm gonna put some materials on Canvas so that you go back and read all of those materials to understand the linear algebra part and the differential equation part. It's okay? So you have something to read to make sure that you can go over, you can understand the rest of the course. So now I'm going to try to solve this problem by exactly the same method, and you see that I can find eigenvalues and eigenfunctions. But in this case, they are not orthogonal. The reason is that this one is not auto-adjoint, self-adjoint. All right? So let us go back to this step one. So the first step is to consider the characteristic equation. The characteristic equation will be x squared plus 2x plus lambda is equal to 0. All right? So this is the characteristic equation. You have phi second plus 2 phi prime plus lambda phi. This is phi 0. All right? So this second will go to this x squared. The constant here is 1. So it's going here to be 1. This is number 2, so it's going to 2. This is order 1, so it's going to order 1. This is order 0, so it's going to act to power 0. And this lambda is going to this lambda. All right? I expand again. Now I have this equation. I have 1 phi second plus 2 phi prime plus lambda phi is 0. So this second is going to x squared. Right? This constant is going to this constant, this number 2 is going to this number 2, this prime is going to 1, this lambda is going to this lambda, and this is 0 is going to this 0. So you understand how to do the characteristic equation. All right? Now, in this characteristic equation, what we do is to consider 3 cases, right? So you're going to have 2 squared minus 4 times lambda, and this is going to give you 4, 1 minus lambda. All right? It's good. Questions? Right. So we're going to consider 3 cases. Case number 1. 1 minus lambda is positive. Case number 2, 1 minus lambda is 0. Case number 3, 1 minus lambda is negative. All right? We're going to go over this on Monday. Questions? Clear?